Hey, this video goes over Investigation 3, Activity 3. So this one is called, Is the Particle Model Always Better? Because we learned that it works better to show what was going on with the ethanol and the water in Activity 2. So we want to find out if it also works for gases. So let's begin. Okay, so question 1, draw a model of what you think air would look like if you could zoom in and see its structure and composition. So we did the same thing with the liquids, kind of thinking about, like, if you were a scientist in the Middle Ages, how would you represent air now? How would you represent gases? So I did mine with just a bunch of different colored circles of different sizes, representing different kinds of molecules in the air. And I wrote, in this model of air, there are different sized particles of different types that are fairly spaced apart. My model of water, ethanol, and liquid had the particles closer together. That's the big difference there. So, like liquids, are gases made of particles? Yeah, they are. Do gases have mass? Yeah, we saw that the balloon that was full of air was heavier than the balloon that was not, that was empty. Okay, so then we were experimenting with some syringes, and this actually, we used the balloon to help us answer this question. So the open syringe is basically similar to like a balloon that's full. It's a syringe that is full of air, right? Whereas a closed syringe, we closed it and then opened it to the same like distance, to the same volume as the open one. But because the closed one was closed, no more air particles got in. So there was a difference in weight between the closed one, which had less weight, than the open one that had more. So the open syringe had more mass. There were more particles in that syringe. So now we're going to make a claim, evidence, and reasoning about this. So the question is gas matter? Our claim is yes, gas is matter. The evidence that we have that supports our claim is that the gas in a balloon takes up space, which is why the balloon looks full, and it weighs more than a balloon without gas in it, okay? So that was pretty easy to see from our demonstration. The reasoning behind that, which is connecting our evidence and our claim to this previous knowledge that we have as a scientific culture here, is that the definition of matter is that it has mass and takes up space. So our evidence shows that the gas in a balloon takes up space, it weighs more than a balloon without gas in it, so that reasoning it fits with what we have here. So then here's our model. Draw a model of the balloons that explains why a full balloon has more mass than an empty balloon. You can see that there are more particles of air inside of that full balloon as opposed to the empty balloon, which maybe has a couple particles of air in it, but not very many. So those particles are weighing down the balloon and taking up space in it. The full balloon weighs more than the empty balloon because the air or gas inside of it has mass and takes up space. Okay? So then we looked at what happens when we fill the syringe with air and close the stopper, and then we try to push the plunger into the syringe. So basically what we're doing is we're compressing those particles there. So the particle model of matter explains what's happening here, because if air is made of particles and there's space between those particles, then that air can be compressed, right? So you can push that plunger in and those air particles are just going to get closer together. But there's definitely a force that's pushing that plunger black out. Like it would like to be this far apart, not this far apart. So the crucial thing here is that gas particles can be compressed together because there is space between them. If we were looking at the continuous model, then everything is like a solid, there's like not space between particles. It's that there's like, it would be like what we look at when we look at water, right? That everything is just like a solid mass, right? But we know that everything is actually made of particles, and we can tell that because when we compress the particle, like we can compress the particles, right, in air. Okay, done. Okay, so starting with the syringe fully pushed in, try pulling back the plunger with the stopper open and then with the stopper closed. So this is where we start with the stopper closed and there's no air in it to start, like it's fully pushed in. And we try to pull it out, with that stopper closed. And it's really hard because there's only a few particles of air in there, and they want to stay the same distance that they are right now. They don't want to be farther apart because air likes to have a certain amount of space around it. It doesn't want to have, it doesn't want to be too crowded, and it doesn't want to be too far apart. But when the syringe was open and that air can flow freely through, then it wasn't hard at all. It just was kind of like normal. Gas particles have a preferred distance that they like to keep from each other. That's kind of the gist there. So we try this with water, and with water, those particles are so close together that you really can't compress it. I mean, I'm sure you could if you had enough force, like a machine or something, but you really can't compress it much farther than that. So I just showed that by copying and pasting the same drawing here with some force arrows showing that I'm pushing it, but really nothing is happening there, right? The particles of water are already pretty close together, so there's not much room for them to be compressed further. So now we're comparing our models for water and for air. How do your models explain differences in observations when you compress water versus air? So water does not compress very much, but air can be compressed with the right amount of force. So there is not much space between the water particles, so there's not much room to compress them. There is more space between the air particles, so those can be compressed. So then we have the simulation. Revisit your initial model of a gas, which was the first question of this activity, which is the one that, that looked like this. This is our first model that we did here. How does your model explain gas compression in a way that is similar to or different than what you see in the interactive model on this page? So here we have a bunch of particles of air, and if I remove the stopper, I can pull the plunger out. All of those particles get in there. I can add a stopper, and then I can push the plunger in, and I can compress it. But you can see that it, I think Concord just froze. You can see that it would rather bounce back out. Okay, so reset. Yeah, Concord has frozen. That's okay, we'll keep going. So my model shows that gas particles are pretty spaced out, so there's room to compress them up to a point. In this simulation, the particles prefer to stay a certain distance apart and create a force if they are compressed. So write a scientific explanation that answers the question, how is it possible to compress a given amount of air into a smaller space? In your explanation, be sure to include the following: a claim, some evidence, and reasoning. Okay, question is, how is it possible to compress a given amount of air into a smaller space? The claim is, gas can be compressed into a smaller space because there is a relatively large space between the particles compared to liquids and solids. The evidence is that I was able to compress the syringe. It was hard, but I could do it. I might even just take that out. I was able to compress the syringe. The reasoning is that air or gas is made of particles that prefer to stay relatively spaced apart. Okay? And that is the end of this one. So thanks for tuning in. I hope this helped, and we'll see you soon.